Hi students, we're back for part 2, and this time we're going to look at the F-test. Now, as we've already talked about, there are ways to evaluate our regression models. We've talked about R-squared. Now we're going to talk about the F-test for overall significance. But before we do that, I want to be very clear. An F-test cannot definitively tell us if our model is good, so be very clear. If you do an F-test, you can't say, oh, my F-test says this is a great model. That is not what the F-test does, as you will see. So our F-test can't tell us if our model's good. It can't tell us if our model is correctly specified. The F-test does need to be done. The F-test is looking at the model as a whole. But be clear about this. It's testing only if your model is better than having no explanatory variables at all. So read that again. The F-test is simply testing if your model is better than having no explanatory variables at all. Gosh, you hope your model is better than having no explanatory variables, right? So hopefully you're starting to think, well, this doesn't seem like a really robust test. It doesn't seem like it sets a very high bar. And if that's what you're thinking, you're exactly right. With this test, we are asking if our model is better than having only a constant. In other words, do any of your explanatory variables or combinations of your explanatory variables have any predictive power? Well, gosh, you hope so, right? Here's basically what we're doing. Let's say that the first yellow box at the top is my model. So some dependent variable y is a function of my explanatory variable x1, x2, and x3. And basically my F-test is comparing that to what's below it. Y is simply a function of our intercept and our error term. Well, if I haven't constructed a model that is better than what's at the bottom, where there's no explanatory variables at all, then I haven't done a very good job, obviously. So as I said, this is not a very robust test. So again, I'm testing to see if these are equally good. Now, let's think about it. As the note in the bottom in the blue box says, if these two things are equally as good, then it suggests that having x1 in my model doesn't help, having x2 in my model doesn't help, having x3 in my model doesn't help. And if they don't help, it's got to be because beta 1 and beta 2 and beta 3 are all equal to 0. Well, if beta 1 is equal to 0 and beta 2 is equal to 0, then beta 3 is equal to 0, then what do I have? I just simply have an intercept and my error term, which says my model doesn't really do much. All right, hopefully we don't have that problem, right? All right, so what we need to do is construct a set of hypotheses. So this is just a hypothesis test, and at this point you already know how to do this. So folks, I'm not really teaching you anything new. I'm just showing you another application of a hypothesis test. All right, so we need to construct our hypotheses. Our null hypothesis is that all explanatory variables have coefficients of 0. All explanatory variables have a coefficient of 0. In other words, they have no explanatory power. Well, we hope that the null hypothesis is not true, right? So remember, the thing that we hope is not true when we're doing hypothesis testing goes in the null hypothesis. Well, then what's our alternative hypothesis? My alternative hypothesis is that at least one of these things is not equal to 0. So I've rewritten the null hypothesis, beta 1 equals beta 2 equals beta 3 equals 0. So they're all equal to 0. And my alternate hypothesis has to be a violation of the null hypothesis. So it doesn't have to be that all three are significant and not equal to 0. It has to be that at least one of them, that there's at least something in my model that has explanatory power. As I said, all we're doing is a hypothesis test, and you already know how to do this. So we're doing exactly what we've done before in other modules. But in this case, we're using a different distribution. Well, this is called an F-test, so not surprisingly, we're using the F distribution. But we also get back a p-value, and you already understand p-values, right? P-values are the probability of a type 1 error, right? Rejecting the null hypothesis when we shouldn't have, when indeed it is actually true. All right, let's take a look at some data. So here's my hourly wage model. And we're not going to worry so much about interpreting this model. We want to jump to the red box. The red box there is where my F-test is reported. So standard regression results is going to spit out an F-test for you. And notice that my F statistic is 433 and some change, right? 433. In other words, it's huge, right? So this is a really, really big number. So this would be akin to having a really big T statistic when we did other types of hypothesis tests with hypothesis testing and regression. So just by eyeballing that, I know I've passed, if you want to say it that way, my F-test. But let's look right below it. It says that the probability greater than F, this is my p-value, is 0.0000, right? So this is like having a teeny tiny p-value, which we know is good. So remember what that tells us. The p-value is our chance of a type 1 error, which means the chance of making a type 1 error is essentially 0, right? Now, not surprisingly, let's jump down to the green box. And what do we see there? We have 3 variables with very high T statistics, right? 14.89, 24.88, 84.42, and probabilities of 0, basically, right? So that tells us these variables, age, male, and of course my constant, really I care more about age and male, but age and male are statistically significant. So if I have results that are statistically significant, my guess is that it's kind of hard to not pass the F-test, for not very precise language, but you know what I mean. So we ran an F-test, we had a huge F statistic, we have a p-value of basically 0. There's no chance of making a type 1 error. Remember what that means, where we reject the null when it's actually true. So in other words, there's evidence that we can reject the null in our F-test. So our outcome here is we're going to reject the null hypothesis, of course, in favor of the alternate hypothesis, which tells us that at least one coefficient is not equal to 0, that there's at least something in the model that has value. So the model that we've crafted with an explanatory variable or explanatory variables is better than just having the intercept, that there's something of value in the model we've built. Again, I want to remind you that this doesn't tell us that our model is good. It doesn't tell us it's well specified. And of course, I pointed to the idea that we had 3 highly significant variables. Well, we actually had a highly significant constant and 2 highly significant explanatory variables. So it's not surprising. I don't think it guarantees that your F-test goes well for you, but there's clearly going to be a connection there. So remember, rejecting the null is a good thing. To be able to say that you've rejected the null of your F-test is important, but be careful about what this tells you. Again, it doesn't tell you your model's good. It doesn't say that your model's well specified. It doesn't tell you if there are omitted variables, that things that were really important in your model that you just failed to include, because if that's the case, your model's not going to be that strong. Or maybe you have irrelevant variables, things you've stuck in your model that really have no business being there. They're not helpful. It really only says your model is better than nothing, right? That's really what the F-test is. And that's why everyone who's doing regression work and statistical work is going to report the F-test. But look, we're not going to make a big deal about it. I'm not going to say, hey, look at my F statistic. I know I've done a good job. Can't say that. All right, so guys, we've looked at 2 measures at this point to overall evaluate our model. We've looked at R-square. We've looked at F-test. I'm warning you one last time to be careful, because neither confirms that you're working with the right specification of your model. It's just important to point them out and to get them out of the way, but then you've got to go on to evaluate your model and really defend the specification. It's important to think about any omitted variables that might cause bias in your model, for example, and our R-square and F-test do not shed any light on that. And there could be irrelevant variables that don't belong in the model, and again, our R-square and our F-test do not shed light on that. As I've already noted, you should report your R-square, you should report your adjusted R-square, and you should give the results of an F-test when you're doing this kind of statistical work. But don't you hang your hat on them. Having a super high R squared and passing your F-test doesn't guarantee that this is really good work. So keep that in mind. If you have any questions, guys, let me know. Otherwise, have a great day and thanks for listening.